I'm very glad to introduce Chris Jospe. Is that how you say it? Chris Jospe from the Negative Carbon Emissions Center at Arizona State University. He works for the world famous Dr. Klaus Lagner, and he's going to tell us not just about the state of the technology, which sounds very promising, and apparently some interesting breakthroughs have happened, but also the policy implications of how an economic way of capturing carbon from the air would change the debate around climate change. So, Chris?
Thank you, Cesar. It's great to see everyone here. Just by show of hands, how many people are in SEPA? Okay. And ESP program? Yes. So I graduated last year in the ESP program. I'm really glad to see the tradition continue. A little bit more about myself. I actually am also happy to see people from the Lenfest Center for Sustainable Energy, which is how I first got connected to this technology and started working for Dr. Lagner. So today I'm going to try to cover what are negative carbon emissions and why do we need them, what is air capture technology. I'm going to contextualize air capture a little bit within carbon management solutions and speak to the near, mid, and long-term deployment prospects for this new technology. I'm very happy to take any questions, like technical clarifications, as I'm going along. And if you have a larger question that you think might turn into a debate or dialogue, please save it for the end. But I know that this is a new technology. Sometimes you can get so caught up with something that it makes a lot of sense to you, and it doesn't necessarily make sense to someone who's relatively new to it. So let's start with this graph. This is basically we're in really big trouble graph from the climate perspective. Those familiar with climate change, we know that the Intergovernmental Panel on Climate Change has said that 450 parts per million is a limit at which we can maybe handle some of the worst effects of climate change. Beyond that, we're not really sure. What we also know is that we're committed to adding about 2 parts per million of carbon dioxide into the atmosphere. Currently, we're sitting at around 400. At current population growth and economic growth rates, that amount can turn into 5 parts per million. When you're dealing with carbon dioxide, it is a very potent greenhouse gas, and a significant fraction of what goes to the atmosphere stays there. So in other words, it's a bathtub, and we just keep adding water in, and at this rate, it's going to overflow. So that's where the Intergovernmental Panel on Climate Change, in its most recent report, said any luck that we have with dealing with climate change will require prolonged periods of negative emissions. If you see this graph, you can see this is the best case scenario, this red line, where we will go up a little bit, and we certainly will overshoot 450 parts per million. That is making some basic assumptions, that no one would be willing to just turn the lights off and go without electricity. Energy systems are path dependent, meaning that once a coal power plant, for instance, is built, X amount of gigatons of carbon dioxide will be emitted into the atmosphere. If you're looking at something that's around 2 gigawatts and it's going to run for, let's say, 25 years, simple back of the envelope will tell you that's 25 gigatons of CO2 that will be emitted into the atmosphere, barring any type of carbon capture and storage. So even if we were to slow down at a very aggressive rate, we still would get there. We would still exceed 450 parts per million. Which is all to say, dealing with climate change requires the ability to become net zero.
Can I ask you a question?
Sure.
Why is 450 hazardous level? Why not 500 or 600?
It's a great question. I'm going to kind of take the political answer. Well, I'm not a scientist, not kidding. Why is it the unsafe level? Actually, if you listen to James Hansen, 350 is an unsafe level, and we already have gone too far. The way climate change works, or global warming, the greenhouse effect works, is that there is a limit. So whether it is 450 or it is 550 or it even could be 600, there is a threshold at which it's too much. I think 450 is helpful for policymakers at this point because it's able to say, well, what can we tolerate? And what do we know, what don't we know? As we get better with climate modeling, it may be that this bar will raise, but nonetheless there will be a bar. So for right now, we'll just take 450 because that's what the rest of the world says. But underlying all of that is that we accept there's a bar. So I put this on here just to show a profile of US carbon emissions, just to speak a little bit to the magnitude of the challenge. You see these first 5, we'll count geothermal as more or less renewable, it's so small, as having no carbon emissions, and then you get to natural gas, coal, and petroleum as the big ones. A significant amount of that goes to electricity generation. You also have a significant amount that goes to transportation. I think to break this up further, you can think in terms of centralized emissions and mobile sources. So centralized emissions, theoretically, can all be dealt with carbon capture and storage. So theoretically, the United States could either turn off these coal power plants or retrofit them at a great cost. The same goes to natural gas, which has about twice or half the carbon footprint of coal. But again, these are power plants that maybe can be dealt with carbon capture and storage. When you get to transportation, that gets a lot trickier. The energy density of liquid fuels is high that we like it. I think we could maybe go into some kind of debate between liquid fuels and electric vehicles, but all of these need to get to zero. And they need to get to zero much quicker than we're doing right now. So, what is air capture? Air capture, I wrote here, is a technology that can capture carbon dioxide from air for reuse or disposal. It's a process that involves 3 basic steps. So the first is, think of a membrane that can come into contact with the air. Sorption on a sorbent, which basically means that the membrane is taking this dilute molecule. And recovery of the sorbent, which means the membrane that's taking the carbon dioxide out of the air is put into a process that it can do this again. There are different ways of doing this. I'm going to speak about one, which I'll refer to as the humidity swing. But in the recovery of the sorbent, you can also do this with temperature, you can do this with pressure. So it's the ability to take 1 part carbon dioxide per 2,500 parts of the air from the atmosphere at up to 1,000 times the efficiency of a tree. So that's basically taking a very dilute molecule from a lot of other molecules and pulling it out. And there's an interesting paper in Nature, and I'm happy to, if you give me your email, I'll send you this, written by Dan Sarowitz and Richard Nelson, called 3 Rules for a Technological Fix. And then it took a look at air capture as an example for a technological fix. So a technological fix is basically the concept that there are some problems that can be solved by technology, there are some problems that cannot. And if a kind of great social problem, or let's look at climate change as a problem, can be solved by technology, then it should meet these 3 requirements. So the first is that it embodies cause-effect and it connects the problem to the solution. So air capture is able to do that because the problem is there is excess carbon dioxide. We don't know what to do with it. The solution is you directly scrub it from the air. This is something that no other sustainable technology can directly do. You can look at renewable energy as part of the solution, but it's not a technological fix because it doesn't take something that is going to be done anyway and stop it. It's only going to offset. It needs to be unambiguous. The reason that air capture is unambiguous as a negative carbon emissions technological fix is because you are able to measure the amount of carbon dioxide removed. When you're planting a tree, you might know that it has a certain percentage of carbon dioxide that is sequestered for a number of decades. But what happens when you stop watching that tree? The tree falls, it biodegrades, and carbon is re-released back into the atmosphere. It gets a little squishier. That's not to say planting trees, not planting trees is a bad idea. I encourage everyone to do that. But as a negative emission, it might not be the best way to measure something. And the last is an important one that says, well, it's technologically feasible, and it focuses on a technology core that can be further developed, and R&D will contribute decisively to a solution. Now, in this case, as in kind of all abatement technology cases, it comes down to cost. Can R&D lead to significant cost reductions? And if so, what does that mean? I just wanted to kind of quickly put this up here to talk about the difference between air capture and carbon capture and storage. Both are relatively new, both are important, and both are carbon management solutions. Basically, flue gas separation, which is conventional carbon capture and storage, is all about taking emissions that come out of a power plant at the source. You'll notice that it is a much bigger machine. It is up to 145,000 tons per day, whereas air capture, we're talking about a modular scale that starts at 1 ton a day. Flue gas comes from coal or natural gas, air capture from air. The CO2 stream, again, what's coming out of the emissions is significantly higher. It can be up to 12% carbon dioxide, whereas we're only looking at 4 parts per million, so 4%. Utilization markets, I'll speak a little bit more about this. I think this is what gets a lot of people excited in the carbon capture, utilization, and storage industry doing things, because they're able to take a waste stream or a resource and make a profit off of it. The first one, which I wrote EOR, that's Enhanced Oil Recovery, will operate over residual oil zones. So this is a tertiary process. So after oil has been kind of pumped dry from whatever natural pressure, and then the second process, which is water's been injected. The third process is if you can inject CO2, then oil will come back up on the other side. This is a big market, and maybe might make a dent in terms of negative carbon emissions, but it's also not a sustainable market. So it's a short-term fix that kind of will enable both of these technologies to move along the learning curve. Another distinction I wanted to make is I said biofuels and biofuels. This one gets an asterisk. I'm obviously biased, so I'll talk about why it's better to make biofuels with air capture first. Algae is a plant that likes carbon dioxide. Algae is also a plant that can be made into a biofuel. It actually needs a lot more carbon dioxide than it can get naturally, or you're running into an enormous footprint problem. Now, if you can get your carbon dioxide from the air and feed it to the algae, you have several advantages. The first would be that you don't have to worry about transportation costs to get the CO2 to you. You can make it right there. The second would be that you're carbon neutral. What you're taking is out of the air, and while it will get emitted on the other side, it's a carbon neutral fuel. And the third is that the locations where it's really nice to grow algae is where there is a lot of sunlight, and where there's a lot of sunlight doesn't always match up to where there is a lot of point source CO2. Now, you can make algae by putting an algae farm next to a coal-fired power plant and pulling off some of that CO2. But by nature, it's this much CO2 if you want to capture all of it, which might overwhelm your algae farm, which won't know what to do with it. And also, while somebody might be able to claim credit for taking that carbon out, that's carbon that's fossil-based carbon, and when it gets emitted, it's not carbon neutral. So the algae, the biofuel that is made from algae, or the carbon capture can claim carbon neutrality, but not both. Another point that's talked about kind of frequently within flue gas is the energy penalty. The Department of Energy wants to bring that down to around 30%. That's to say, if we were to put carbon capture and storage on all the centralized electricity sources, that your electricity prices would go up by 30%. That's because you need to spend more energy actually capturing all the carbon dioxide. All right, so let me talk a little bit about the work that I'm involved with. So the moisture swing. It basically, so when we talked about the three processes, you've got contacting air, you've got sticking to a sorbent, and you've got recovery of that sorbent. Here's a picture of what we'll call the shutter box. On one side you can see a membrane that is exposed to air, and on the other side it's a little bit dim, but you have another one that's in an enclosed area. The way it works is it's able to capture carbon dioxide when it's dry, and when it's down in this box, the moisture content is significantly higher, and it will feed off that carbon dioxide. This is a passive way of capturing carbon dioxide. The only energy that's really spent is the frictional energy that's moving these shutters back and forth, which is significant to think about when you're comparing the energy penalty of flue gas capture. What's also important to note is by doing this, you can take something that is in the atmosphere at only 0.04% and raise it up to around 11%. So you haven't generated pure CO2, but you do have CO2 enriched air, which is something that is quite favorable for biofuels or growing in places like greenhouses. Now, if you scale it up, this is an artist's rendering. That the same idea kind of has this fan that would spin around, and this area would have some moisture. So here you've got these membranes as contacting the air, and as it goes down, it's feeding CO2. This is such a unit that doing back-of-the-envelope calculations could capture at around 1 ton of carbon dioxide a day for starters, and probably get up to 5 tons per day. You'll notice that it's the size of a shipping container, which is an important argument that I'll call comes from the Lochner philosophy, which is to look at economies of scale, which is to say, to really scale up and to do something quickly, because we're talking about 1 ton a day units. And there are a lot of tons of carbon dioxide. There are actually about 36 gigatons. So if you have something like this capturing 1 ton a day, just do some math, multiply by 365, you would need 100 million of them to deal with all of mankind's emissions. That's a lot. But to think about how many shipping containers go through the port of Shanghai, for instance, it's only 80 million per year. So you'll see that it's not on a magnitude that is infeasible. And by sending shipping containers, you're able to quickly move to locations that are most favorable. So, jumping around a little bit, but let's go back to the carbon dioxide markets. Again, the whole point of this technology is to occupy a market that can teach you something that will let you bring down costs to get to a point where you're taking something from air and putting it away and disposing of carbon dioxide. So the first would be merchant CO2. These markets are small and distributed. The CO2 price is often quite high. And people will sometimes pay up to $300 per ton of carbon dioxide. This is a great example of why if you can get something from air and feed it to these small markets, that you would have a market advantage. Chemical commodities such as urea require CO2. And urea facilities are actually quite often located next to point sources. But if you're able to think about farming from remote perspective, you have significant advantage by also creating urea in some of those remote areas. Biomass production, I already spoke about this, but the greenhouse market is an interesting one that is flourishing quickly. Greenhouses, plants, photosynthesize, and plants like carbon dioxide. So if you're able to feed more carbon dioxide to these plants, you're actually increasing the yield, and plants grow bigger, better, faster. What's also interesting about the greenhouse market, by feeding CO2 from air, is you're giving them a pure stream, and greenhouses will currently buy compressed CO2, which costs them a lot of money. Enhanced oil recovery, I spoke about this, but when there's no pipeline or it's a really remote area, this will be able to get CO2 to that market. Synthetic renewable fuels, this is something that the Lenfest Center has thought a lot about. Synthetic fuels is basically, make this as not least technical as possible, but it is taking the carbon dioxide from the air, pulling hydrogen from water by zapping it with electricity, and using the C's, the O's, and the H's to make a liquid fuel that can be used just like methanol. This is a great process because if you're using renewable sources to zap the hydrogen, then it's a carbon neutral fuel. And it's an interesting way where if you're able to think about, and I'll speak a little bit at the end of scenario building, but if you can conceive of a scenario where you've got distributed sources of renewable energy, that might need a storage buffer because the sun doesn't shine all the time or the wind doesn't blow all the time, then this gives you a way to make a fuel that has a high energy capacity. Not to mention, you're no longer drilling for gasoline. This is expensive. The cost barrier is not necessarily the CO2, but it's actually the electrolysis process. And then sequestration. This is a big market, and this is an exciting market because this is where you would be able to say, I am carbon negative. And in the long-term picture that we're trying to put forth, is you are able to provide a certificate that says, well, you're unable to completely become carbon neutral, but you know that you have to, so you pay. And this probably sounds very familiar to you. It goes back to carbon, putting a price on carbon. So I just put up 4 companies just to talk about this because it's, didn't get your name, but right before we were speaking about something called the Virgin Earth Challenge, which was put out by David Addison, which is basically a $10 million prize for the first company that is able to show that you can take 1 gigaton of carbon out of the atmosphere. Several companies entered that. One of them was supported by my boss, Klaus Lochner, as well as somebody who works in the lab with us, Alan Wright. We've currently taken a more academic route to not be on the commercial end yet, but be on the more umbrella end of developing this technology. But Carbon Engineering is a company that's in Alberta. They are looking to create carbon dioxide for enhanced oil recovery, first and foremost. But they're also looking at co-locating with areas that need it. Global Thermostat is led by Dr. Peter Eisenberger, who's at Columbia, and Graciela Chichelinski, who's also at Columbia. Graciela is actually someone who played a really big role in cap and trade in the Kyoto Protocol. They're located in California, and they are interested in EOR as well, but they also look at biofuels. They use heat as their source. Climeworks is an interesting company in Zurich, Switzerland. They just partnered with Audi, the car company, to make synthetic fuels. So this is promising for them, and we partner with them and hope that they can do it right. Infinitree is another partner of ours. Infinitree uses the moisture swing to feed carbon dioxide into greenhouses, and they're also looking to grow biofuels in those greenhouses. Does anyone have any questions about these companies? Okay.
Can you go back? If this is like holding you back, never mind.
No worries. I'm happy to just tell you later. So, let's talk a little bit about costs. In 2011, a study came out that was put together by the American Physical Society that basically said, all right, so air capture seems to be a serious idea, but we need to put a cost on it. And what would a first of the kind look like? The report came out and said, we don't think it could be done for less than $600 per ton. On the one hand, this was kind of crippling to the air capture community because $6 a ton, if you price that at the pump, it would come to about $5 per gallon of gasoline, which is politically impalatable. But there are several reasons why that study is overly pessimistic, if you will. And I think the kind of unscientific way to describe it is to say it looked at penguins and made a conclusion that birds can't fly. So the technology that we're working with, the first of a kind, actually had cost estimates between $200 and $300, and now current estimates were down here, where CO2-enriched air, which is not a pure stream of CO2, is even cheaper, where the raw energy limit, which is the frictional cost, could come down to as low as $30 per ton. And if you look at other technologies that have started out very expensive, it's not inconceivable to think that prices can come down. So solar panels, for instance, have come down 100 times, or 100-fold, since they were developed. in the 60s. So here's the challenge. This curve is the cost of the technology, but there's no way, but there is not a seen way that we're necessarily on this cost of technology yet. And we need to bring the cost down. If the costs never come down, and they always remain high, well, they'll never be able to deal with what we'll call here the social cost of carbon, which is future damages from climate change. The Obama administration not too long ago asked for new numbers from the Department of Energy, would put $35 a ton per, or $35 per ton of carbon dioxide emitted. Which is a nice number to shoot for, but because that's so expensive, and because this technology hasn't been proven, there need to be ways to bring this cost down. That goes back to the merchant markets, but that also needs to look for people that say, let's pay more right now so that we can bring the cost down. And as that cost come down, what you've done is you've saved future generations from having to pay way more. And that concept is to say, well, in the long term, I'm going to skip that and go here, because I know we don't have that much time. In the long term, you are providing certificates that shows that carbon dioxide has been put away. So, to get a little economic-y here, this would put a price on carbon. And this would be a scheme that would enable carbon dioxide to work, or air capture to work within a price on carbon. It would set a desirable amount of CO2 emissions, and the desirable amount, I think, or I hope that I can convince people in this room, is 0, and we need to get there. And the way that you could convince people is to say, well, you can emit a little bit, and you can have a certain amount of emissions, but at the end of the day, what needs to be taxed, or what needs to be accounted for, is fossil carbon that's coming out of the ground. Because this is new carbon being released into the atmosphere. So, either you can deal with that from CCS, or you can deal with that from air capture. But air capture becomes the most expensive option that motivates other sustainable options. So to put it differently, it would be like saying Jane has a carbon footprint of 10 tons, and we're going to price that at $30 per ton. Jane can decide not to drive her car and bike to work, and that would then bring her carbon footprint down to 9. And she can decide to make emissions reductions in her house, which will bring her down to 5. And then she could decide to, I don't know, put a solar panel on her rooftop, and she's down to 3. But she still needs to deal with those 3 tons in some way, and then Jane would have to buy a certificate of sequestration. I'll end here, just because I want time for questions. But the concept is building a net zero scenario. How do we get there? Addressing climate change, there's no one silver bullet, and I'm not trying to stand here and tell you that air capture is the silver bullet. But it can become a tool that changes the conversation. By having the ability to suddenly say, we can deal with your carbon emissions, allows you really to think, well, now we can think in terms of net zero. So these, call them synthetic trees, have been associated with my boss for a long time because it's kind of a way to say, well, here these things go out, are capturing carbon dioxide in the atmosphere. They enable carbon neutrality through making liquid hydrocarbons like this. They allow a family that has a carbon footprint, like that big chunk of coal in their front yard, to completely offset it. And they allow a carbon closed loop system to kind of streamline and advance the development of this technology through greenhouses, fuels, or even enhanced oil recovery or sequestration. I just wanted to show one picture. So this is Ernest Moniz, who is the U.S. Secretary of Energy, talking to my boss. And it is basically to say, air capture works, it is thermodynamically possible, and Ernest Moniz said, great, prove it. So that's what we're trying to do, is to really demonstrate that air capture technology works and that costs can come down. So we have a prototype which is operating continuously outside. This is something that over time will increase from having a footprint of just taking maybe 10 kilograms of carbon dioxide out up to 1 ton. This means increasing the scope, sophistication, reliability, efficiency of these systems, and it requires a number of different sciences, and it also requires what I'd like to coin as TESPIA, which is where a lot of the policymakers should think about this. But what's the techno-economic, socio-political, environmental assessment? So when you're thinking about this technology, there are all sorts of trade-offs, and there are trade-offs. And how do you think about this system in the context of other systems that might have different pros and cons? So I'll stop there, and I'm happy to answer any questions.
So what's the status of it? We have a prototype that is working continuously. So in order to make it, let's say, to solve the problem, you have to make it larger, you have to make it more efficient, you need more investments, you need more technological, development. What's needed?
Yeah, you sort of answered the question.
A little bit of everything.
A little bit of everything. I think I'll answer on the technological level first, but I think there are many different pillars to answer here. On the technological level, there needs to be an unambiguous basis for costs. This is something that you can learn through optimum inputs. So that might be what's the temperature, what's the humidity, what's the moisture content, how big is the material. And as we prove that this works, it takes gaining acceptance within different communities. One community is the carbon capture and storage community, which says, this will never work, it's so much more dilute, coal has 300 times more carbon dioxide, let's start there. And then they will look at something called Sherwood's rule to substantiate that. Sherwood's rule essentially says that cost scales linearly with dilution, meaning that if something is 300 times more dilute, it might be 300 times more expensive. So part of our argument is to say, no, that's not true, because we're able to passively capture the carbon dioxide from the air, which allows you to overcome these barriers. So what's needed is acceptance, and as we continue to prove that, which means, well, we did it at this scale, and we've done it at a bench scale, and then we do it at something that's even larger. Where's the threshold, and when does that break down? And I don't think it will happen overnight, but I think increasingly, which gets to the other side of that, which is the policy level. So on the policy level, there should be incentives for the new carbon market. So technologies just like solar, which have this obvious advantage to deal with things in a sustainable way, could really benefit from having any sort of incentive that leads toward this pathway. I think it's time. I think we're very new. We've showed up at ASU in September, and we are just starting to build things on the scale that is much bigger than they were at Columbia. So all that's to say, I think I was telling Cesar, part of me feels like a snake oil salesman, because I'm telling you something that works, or that should work. But I'm reluctant to put the cart before the horse, which is that we need to prove. But on the other hand, we don't have time. So if we already cast a bet, this is a good bet to cast that costs can come significantly down. Yeah?
Are there any studies available given the skill that we need to make defense on climate change on the kind of economic costs for the infrastructure to transport and also store the carbon?
Repeat the question.
Skill that's necessary to actually make the dents on the carbon emissions that we emit. But how about the actual infrastructure, pipelines, supply chain routes that we actually transport the carbon?
That's a very good question. So the question was, are there any studies available that kind of take a broad view of the costs? I have, for people who are interested, a one-pager. There are 2 selected publications. One of them was a paper that showed up in the Proceedings of the National Academy of Science called The Urgency for the Development of CO2 capture from ambient air. That's a great jumping off point that looks at cost projections and kind of what needs to get done. But this is something that's so new that we can't talk about infrastructure if we haven't built the device. So absolutely, piping is key. And carbon capture and storage needs to think even more about piping. And there are many different methods and ways to once you have carbon dioxide, actually do something about disposing of it. So to think through some of those studies. But it's a good, and so it's ongoing, and it's a field that needs a lot more thought.
How do you think? What do you think is the role of public-private partnerships to make this technology more affordable, and at the same time, maybe a joint partnership with biosequestration? Because some countries, like Brazil, is also an alternative for carbon sequestration.
Yeah. So public-private partnerships is a great word and a great concept, and is needed for this, just like all sorts of sustainable development. I mean, first, what you need is a price on carbon, and without that, the public sector is not going to underwrite the cost of this technology. Once you can get into saying, here we are and we're delivering a public good, then you've got a really interesting model. And I think the ideal partner for that is actually the electric utility. Doesn't need to be the electric utility that is emitting CO2, but that thinks of itself as the utility of the future, which is to say we'll scrub carbon dioxide out of the atmosphere, which is a public good. I think one part that being at a university that's trying to coalesce other universities, that affords the ability to make industry consortia, which is something that we're thinking about, and is a way that allows you to bring some of the best knowledge into working on various components of this technology. I think once carbon utilization really gets launched, then you need the public to talk about it. You need people to vote for that. And I think that will emerge even more. I think it goes back to like your question, we need to demonstrate kind of beyond proof that it's an investment worth making. So there will be the early adopters, there will be the strategics, there will be the venture capital that goes into that. And if the venture capital is right, they've placed an enormous bet that will pay off because a lot of this will be needed. And then hopefully it spirals.
I think that's about all the time we have. Thank you very much, Chris.
Thank you. It's a pleasure.